Hello everyone, in this video we're going to be talking about how to determine the melting point of the compound and mixtures. In addition to that, how to use melting point to determine the purity of the compound and also to determine the unknown compound from in a given sample. So to begin with, let's talk about what a melting point is. So melting point is going to be the temperature when your liquid phase of the matter and the solid phase of that matter are going to be in equilibrium. Or another way of saying, your solid is about to be melting into the liquid phase, or your liquid is about to be freezing onto the solid phase. It's a physical property where the identity of the material really doesn't change. So when we melt something, you're not really changing the identity. You're still going to have the same compound, but just in different phase. We can use this to figure out the unknown compounds because organic compounds have a very sharp and unique melting points, but that doesn't necessarily mean you won't have two organic compounds having the same melting point. You could have the same melting points for multiple organic compounds, but you can still determine if you have a given unknown compound by using the mixture method. So we'll talk about that in a minute. Most organic compounds will have a sharp melting point, and the typical range for this is 1 to 2 degrees Celsius. If the range comes out to be, suppose 4 or long or over, even 3 or over, that technically means your compound is impure. It has some impurities in there. For the most part, you should have a sharp melting point ranges from 1 to 2 degrees Celsius. If you have an impurities in there and those impurities needs to be the soluble impurities, what does that really mean? We're not really dissolving anything in water here or in a liquid. How can something be soluble in the solid? Well, whenever you have the impurities, it must be making some sort of interactions with your unknown or with your pure compound, and that's when we call it soluble impurities. And if you have a soluble impurity, it's almost always lower the melting point, and it's also always going to broaden the melting point range. So we talked about the melting point range in typically 1 to 2 degrees Celsius. If you have an impurity in there, it could be anywhere between like 10 to 15 or even bigger than that, depending on the mixtures and the type. However, if you have an insoluble impurities, such as suppose you have a paper or a dust or maybe sand in your sample, and that sand really doesn't interact with your compound. It's just there, but it's not really making any sort of interactions. So in that case, the melting point is usually not affected. You may see that dust or sand if they have a higher melting point than your compound. Once your compound is melted, you may see those particles kind of floating in the solution, but that's just the sand or the impurities that you got in there that's not going to be soluble in the solid, and they're not necessarily affecting your melting point. Now, how does that impurities really work? So if you have a compound, suppose I got a compound that has the solids in there, so they're making some sort of interactions in there. So you want to break these interactions before they can go into the liquid phase. But then all of a sudden, if I throw in a impurity that's soluble in the solid, that means it's going to be making those interactions with your pure compound or your main compound. So when it's making those interactions, at what temperature they're going to be breaking in will be different than at what temperature your known compound interactions will be breaking in, and that's why your melting point range is going to be broadened in that case. The melting point is a function of molecular mass. The higher the molar mass, usually will give you a higher melting point. The polarity is a big factor, the type of intermolecular forces and surface area. So they all actually determine what's going to be the melting point. When you're determining the melting point using the melt temp, that's a usually commonly used apparatus. When you when you know the rough range of the melting point of your compound, you can ramp your temperature quickly until you reach below 20 to 25 degrees Celsius than the actual melting point of the compound. But then after that, or when it gets closer to the melting point of your compound, you want to increase the temperature very slowly so that you can get a very good reading for the melting point, usually 1 to 2 degrees Celsius per minute in that case. If you do it quickly, you're going to be getting a false melting point. How do you really use melting point to figure out the unknown? So suppose I have these two compounds. One of them is benzoic acid that has the melting point of 122 to 123. Then I got two naphthol here that's got 120 to 122 degrees Celsius. So they both have very similar or about the same melting point, obviously different compounds. And then you're given a compound A, and this compound A happens to be melting at 121 to 123 degrees Celsius, suppose. Now I can't really tell just based on the melting point if you're going to have a 2-naphthol or a benzoic acid, because they both have very similar melting point or almost the same melting point. So what can you do to figure out if compound A or unknown A is indeed 2-naphthol or in a benzoic acid? You can make mixtures. So let's say I want to make mixture 1, and in mixture 1 I want to have unknown compound A plus your benzoic acid. Now in this case, you may want to make your unknown compound A to be the main compound, and you want to add a little bit of a benzoic acid, so kind of acting as an impurity in that case. And then make sure you mix these two well, take the melting point, and if the melting point comes out to be 121 to 123, or like in a very narrow range, that means your unknown compound is indeed going to be benzoic acid. Now to make sure it isn't a benzoic acid, you want to run in a similar experiment where you make this mixture 2, and in the mixture 2 you're going to have an unknown A, and then you're going to be adding a little bit of a naphthol in there. Okay, so when you're adding or making the mixture of those two, again, the naphthol needs to be an impurity, so make sure you add just a tiny amount of that. When you mix those up, take the melting point, and if your unknown A was indeed the benzoic acid, the melting point of this mixture 2 is going to be a very broad range. It could be something like 100 to 112 degrees Celsius. So that tells you that those two compounds, unknown A and the 2-naphthol, are not the same molecules, because first you have broadened the range, and then second you have lowered the melting point. And then if you have more than two, you're going to be doing the same thing. Suppose you have another compound that has a very similar melting point, then you would have to make another mixture of that compound to figure out if that gives you a sharp melting point and the same melting point, or that gives you a lower and broad melting point. So that's how you're going to be figuring out the identity of the unknown compound using melting point. Now let's talk about another common term that's usually used when you're dealing with the melting point labs or learning about the melting point, is the eutectic temperature and the composition. The eutectic point or temperature is going to be the lowest melting temperature when a mixture of two solids in any ratios will melt, or will start to melt, rather, not melt all the way. So suppose, let me give you an example. It's going to be confusing, but I'm going to break it down using an example. Suppose I have X and Y as my two compounds, and the melting point for X is 121 to 123 degrees Celsius. The melting point for Y is 112 to 113 degrees Celsius. My job is to figure out what's going to be the eutectic temperature and the eutectic composition. Now, finding a eutectic temperature is not that hard. Finding in a composition, you have to be lucky because different mixtures will have a different eutectic temperature and different eutectic compositions. So suppose I have this graph here where on the x-axis I got the mass percent of x and y. So on the top line here it talks about the mass percent of x, where on the beginning here, so I'm going to change the color here, on the beginning here you have mass percent of x is 0. That means all you really got is the y, which is going to be 100% y. And at that point, and if you have a mixture like that, it will have only y, so you will see a sharp melting point for the y. And remember, the melting point for y is going to be 112 to 113 degrees Celsius, and that's going to be right there. And then on the other end, we can say if you only have the x, so here you only have the x, and there's no y in that particular mixture, then your melting point is still going to be sharp because there's only X compound in there. And in that case, the melting point is going to be 121 to 123. In between, where you're going to have the mixture, your melting point is going to be different. It's going to have a broad range and it's going to be actually lower. This, I just made a graph. When you do the experiment in the lab, it may not necessarily follow the same range, but just for the example purposes, I have said this is what it kind of follows. So wherever they meet, this is going to be your lowest temperature here. So at this lowest temperature, that's where both those solids going to start melting, or that's called the eutectic temperature. So this is going to be your eutectic temperature right there. And whatever the composition you're going to have at this particular point is going to be your eutectic composition. So this right there, it's kind of roughly 40 to 60. Not exactly 40 to 60, but for the sake of calculation, so I could take that as 41%, and then in that case, this would have been 59% as your eutectic composition. Now, like I said, eutectic temperature finding is going to be relatively easier. Eutectic composition, you may have to plot the graph to figure out what that's going to be. Suppose, let me give you an example here and see how you really deal with that. Suppose I have a mixture of 100 milligram sample, and in that 100 milligram, I got 20 milligram for the X and 80 milligram for the Y. We are looking at 80% Y, which is going to be this right there, and 20% X, which is going to be this right there. So it's a good idea to be familiar with where you at in that particular case. And then out of those two, one of those is going to be impurity. So whoever is actually less in amount is going to be your impurity. So this one is going to be the impurity. So now suppose you mix those X and Y well, and you put them in a capillary tube, and then you put them in a melt temp apparatus. Now you start observing when they're going to start melting. So this mixture, suppose it starts melting at, I can say maybe 95 degrees Celsius. So that 95 is actually going to be your eutectic temperature. That's going to be your 95 degrees Celsius there. Now at 95 degrees Celsius, your X and Y, they're going to be in equilibrium with their liquid phases. Since your X is the impurity and they are less in amount, your 95 will stay there until all the X has been melted. So once all X is melted, you got to figure out how much Y is left over. So you're going to have 20 milligram of X is melted, and then figure out how much of the Y is going to melt. Now I know the eutectic composition is 41% X and 59% Y that we just rated off from the graph. So to figure out how much Y you're going to have left over here, I can go ahead and multiply with 59 of Y, 59% of Y, or you can say 59 milligrams of Y, and divided by 41 milligrams of X. So that's how you always going to be finding what's going to be left behind at the eutectic composition or at the eutectic temperature when you are doing the mixture. So you always take the ratios of the eutectic compositions. So it's going to be 20 times 59 divided by 41. That gives you 28.78 milligram. So at this time, or whenever the 20 milligram has been melted for the X, 28.78 milligrams of the Y will be melted. So how much is left over? Well, we started out with 80 milligram minus 28.78 milligram. So we're going to have a little bit over 50, seems like. We got 51.2 milligrams of Y still left at that particular temperature, at that eutectic temperature, once all that X has been melted. Now, from this point on, how the melting point is going to look like, or how broad the range going to be, I know initially we're looking at 20% X and 80% Y. So I can go ahead and draw a line there and see where that meet on that particular graph. So that means this remaining 51.2 grams of Y is going to melt starting at a temperature of 95 degrees Celsius until this temperature right there, which could be anything. Well, it's going to be a little bit less than 112. So if I just make up a number here, because I didn't really draw this on the scale, I can say this will be 106 degrees Celsius. So you will have a broad melting point for this particular mixture starting at 95 degrees Celsius all the way to 106 degrees Celsius. So once it reaches 106 degrees Celsius, all the remaining Y will be melted. And then you can also have the otherwise. You could have the Y to be the impurity and the X to be the main compound. And in that particular case, your graph will go onto the right side because that's where the main compound is. Now, you have these four sections, and it's important to kind of understand what's going on in those four sections there. I got, let me call this section A, section B here, C here, and D here. So on section B, you're going to have both solid X and Y, or both of your compounds going to be in solid. As the temperature reaches the eutectic, that's when you're going to have something start melting. Now, when you're on the side A, what's on the side A? Well, we have Y to be the main compound and X to be the impurity. So you will have some solid. So on this side right there, you will have some solid Y plus you'll have some liquid X and Y, because remember some of your Y was melted at the eutectic point based on what was the eutectic composition was. And then the same story on C, you will have solid X plus liquid X and Y. Because remember, if you have your X to be the main compound and Y to be the impurity, at eutectic temperature, all the Y or all the impurity will melt, and then some of the X will also melt based on the eutectic ratio there, and the remaining X will be melted along this line here. Now in this section D here, this is where you're going to have both to be both to be liquid. So you're going to have a liquid X and liquid Y there. So that's how you're going to be reading this graph here. The next question I would do want to ask you guys, can you ever have a sharp melting point when you have two solids in the mixture? Well, technically you could. It's going to be very rare, but it's possible. If you have X and Y, like in this particular case, and I somehow mix exactly, let's say 41% of X and 59% of Y, because that's your eutectic composition. If I make a mixture that's exactly at the eutectic composition, then that particular mixture will melt sharp at the eutectic temperature. And sometimes it's usually taken as a false pure compound, even though it's not a pure compound. That's something you got to be really careful with. It's unlikely to happen, like how likely it is to have an exact ratios of those two compounds that's going to be making up the eutectic composition. And to begin with, if you're dealing with two compounds, any two compounds, you don't even know what their eutectic composition is going to be unless you do some experimentations and make this graph and figure out where that's going to be. All right, if you have any questions, feel free to leave any comments in the section below.